Okay, so we hear the term machine learning just about everywhere these days, right? But what does it actually mean when we say a machine can learn? I mean, how does something made of silicone and code even begin to think? Well, in this explainer, we're going to demystify that very idea.
So let's start with the most fundamental question of all. How can a computer, which is really just a piece of hardware running code, go from just following commands to actually learning from experience? It's a pretty mind-bending concept that has fascinated scientists and philosophers for decades.
You know, if we boil it all down, learning is a pretty simple idea. It's just changing your behavior based on experience. And that applies to us, to animals, and to the algorithms we're talking about today. The only difference is, for a machine, that experience is data. Lots and lots of data.
Right, so what exactly is machine learning? At its core, it's all about teaching a computer how to find predictive patterns by looking at observations. You see, the old way was to program explicit rules for every single possibility. The new way, we let the machine figure out the rules for itself.
A great way to think about it is as this perfect marriage between two massive fields. You've got statistics, which gives us the theory to understand data and probability. And then you have computer science, which gives us the raw power to process all that data at an incredible speed. You put them together, and you get this amazing ability to turn data into really powerful predictions.
So one of the most popular ways machines learn is with a teacher. This method is called supervised learning, and that teacher is basically just an answer key, a whole bunch of data where we've already labeled the correct answers. And this slide really nails the two main approaches. With supervised learning, you feed the machine labeled data, like a million pictures of cats that are all labeled cat. The whole point is to get it to predict the label for a new photo. But with unsupervised learning, you just dump a massive folder of unlabeled photos on it, and its job is to discover patterns on its own, like maybe grouping similar-looking animals together.
Now, within supervised learning, a huge category of problems is called classification. The goal is pretty straightforward. Assign something to a specific category. Is this email spam, or is it important? Is that handwritten scrawl a 7 or a 1? Is that a picture of a dog or a cat? All of these are classic classification tasks.
The other major type of supervised problem is called regression. Here, instead of picking a category, the goal is to predict an actual number, a continuous value. So we're not asking if a house will sell, we're asking for how much. We're not just trying to predict if a stock will go up, but by what price. It's all about predicting a number on a spectrum.
Okay, but what happens when there's no teacher? What if there's no answer key to learn from? This is where unsupervised learning comes in, and this is where things get really interesting.
With unsupervised learning, the algorithm has to dive headfirst into this giant ocean of unlabeled data and find the hidden structure all by itself. I want you to imagine giving a machine a giant mixed-up box of Legos and just telling it to sort them. It has to figure out on its own that there are different colors, different shapes, and different sizes, without ever being told what a red brick is.
A really common way this is used is through something called clustering. And it's used for all sorts of things. It's how image compression works, by grouping similar colored pixels together. In medicine, it's used to find groups of patients who have similar symptoms, which might point to a new subtype of a disease. It's all about finding those natural groupings that we might not see ourselves.
So how does a machine actually do all this stuff? It sounds a bit like magic, but it's not. So let's peek under the hood and take a look at two key algorithms in the AI toolbox to see how they actually think.
Okay, let's take a simple classification problem. We've got two groups of data points here, right? The blue X's and the orange plus signs. Now, you could draw, literally, an infinite number of different lines to separate them. So how in the world does the machine pick which line is the best one?
This is where a really clever algorithm called the support vector machine, or SVM, comes in. What it does is it finds the data points that are sitting right on the edge of each group. Those are the support vectors. Then, its whole goal is to draw a line that creates the widest possible street, or margin, between them. This gives us the most confident and robust separation possible. It's just a really elegant solution.
But what happens when the data doesn't look like two nice, neat blobs? Real-world data is messy. Sometimes the patterns are weird shapes, like long and thin, or even donut-shaped, like we see here. So how can an algorithm possibly find these complex groups when it doesn't even know what it's looking for?
Well, this is where an unsupervised algorithm like dbScan shines. It's a bit of a mouthful, but it stands for Density-Based Spatial Clustering. And as the name implies, it thinks in terms of density. It finds a point, looks for its neighbors, and if there are enough of them close by, it decides it's part of a dense cluster and starts expanding. This simple idea lets it find clusters of practically any shape, like the rings we just saw.
Okay, so the machine has processed all this data and it's built a model. Awesome. But this brings us to probably the most important question in all of machine learning. Has it actually learned, or has it just memorized the answers?
Think about it like this. Imagine a student who's studying for a test by just memorizing every single question and answer on a practice exam. Yeah, they'll get 100% on that practice test, no problem. But does that mean they've actually learned the material? What's going to happen when they see a brand new question they've never seen before? This is a massive problem called overfitting. It's what happens when a model gets so complicated that it doesn't just learn the pattern, it actually memorizes the training data, including all the random noise and weird little flukes. The result is a model that looks like a genius in training, but the second you show it new data from the real world, it completely falls apart.
So how do we solve this? The answer is validation, and this is absolutely non-negotiable. You never ever use all your data for training. Instead, you split it. You train the model on one part, the training set, and then you test how well it performs on the other parts, the test set, data it has never, ever seen before. That is the true test of whether it has actually learned anything.
And this really gets right to the soul of what machine learning is all about. The goal isn't just to find patterns, it's to find patterns that generalize, patterns that are true for new, unseen data in the future. That, right there, is the difference between simple memorization and genuine intelligence.
Which leaves us with one last and pretty provocative thought to take away. This technology is incredibly powerful, and it's getting more powerful every single day. So the most important question we have to ask ourselves isn't can machines learn anymore? It's what should we, their creators, choose to teach them.